All right. So good morning. Today we're going to kind of plow through this. Going to see a couple things what I can do here. There we go. Unfortunately, this is the only way I can do this. I can't write on Smart Notebook, and up here, and to transfer it onto like a PowerPoint is almost impossible. So I just wrote on the sheet. Why don't we have our note sheets out? We had like 7 minutes. 7 note sheets out, please. We've had a lot of time. All right, so we're going to see how much we can get done. Yesterday we kind of talked about the electromagnetic spectrum. We filled it in. We talked about some things on the right, wavelength, frequency, all that good stuff, and some of that relationship. But we also need to kind of discover some other equations and kind of the origins of where they kind of started from. So here we go. I'm going to do the best I can to kind of help you along with this. So the first really important scientist was a guy named Max Planck. You've heard of it because of Planck's constant. Okay, he came up and he contributed this equation, E equals h times nu, which is Planck's constant times frequency. And what he had talked about, and we discussed this a little bit last year, is about that there's these pockets of energy that actually exist. It's not this fluid motion. It's not a ramp. It's more like stairs or steps. And objects emit energy in the form of these small packets of energy, and they call them quanta. So like there's a show when I was a kid, it was an awesome show called Quantum Leap. And this scientist would leap into the past, into other people's bodies, and correct what went wrong and made it right. But he always jumped, and that's kind of what happens. Electrons jump, and then they release this energy. Totally unrelated to the sci-fi show, but anyway. An unknown scientist named Albert Einstein came up with the whole E equals mc squared. I have it's on my closet door behind my desk, and it's Albert Einstein in the front of a chalkboard, and it says like E equals mc, and then there's like a 7, E equals mc, and there's like a 4, E equals mc, there's a 3, and then like, I don't know who it is, someone's cleaning his desk, and he's like, yep, there we go, everything's square, everything's squared away, everything's squared up on the desk. And Einstein's all frustrated at the chalkboard, so kind of a funny little cartoon. But what he brought to the table in all this with radiation and energy was radiation itself is really a stream of particles called photons. This is a big deal because people saw light and they just thought it had nothing of substance. And what he was trying, and what he brought to the table was that there's actual particles. Unfortunately, ours is broken. You could have like a cathode ray tube, and when you send energy through it with like a Tesla coil, you can put an object up in it, and it stops it. Well, it makes a shadow. Well, it's actually blocking those particles from moving forward, and it can kind of illustrate his contribution there. And then the last one, Louis de Broglie. I don't speak French. Or actually, I do a little bit. Ready? Ho ho ho. Yeah, I know. It's native tongue. It's very good. Madame Nichols and I showed her that last year, and she was very impressed. So he brought to the table, by the way, this is actually a V, which is going to get a little confusing. Wavelength equals h over m times v, so mass and velocity, how heavy something is and how fast it is going. He brought to the table that matter has both particle-like and wave-like characteristics. Now, this is very much in the physics realm. Underneath, I kind of drew what he was talking about. It has particles, so like billiard balls, like it has mass and it has volume and it has inertia and all that. But it also acts like a wave. So it has peaks and troughs and brings energy and wavelengths to the table as well. They do both. And there's a lot of layers to this that we're not going to get into, but these are kind of the three gentlemen that kind of brought a bunch to the table that gets us to where we are today. So I made a nice little flow chart. Hopefully you'll be able to understand it. So let's start from the top right here. If we take, and Einstein contributed a lot to this, if you take the fact that wavelength and frequency equal the speed of light, we rearrange that. And then we take Planck's contribution, and you combine them. That's that combined equation that we have known to use. right? You can figure out energy based off of a wavelength. So far, all this is the same. And your responsibility, I have to be able to figure this out and get the derivative of each equation. No, although we have done this part. Then, if you take that idea, this is the problem. I can't hide anything from you here. I wish I could more. Then you take that equation, and then you think about Einstein's equation. They both equal E. I just want you to recognize that. Like if they both equal E, I can make them equal to each other. Okay, so there's Einstein's, and there's the combination of Planck's and wavelength and frequency. And when it's all said and done, that's how we get de Broglie's equation, which is our new equation for this chapter of this section. All the other things we have seen at some point. And if we need to refresh, that's why we kind of did the review sheet. But it's wavelength equals Planck's constant over mass times velocity. Now, a lot of times physics teachers will make a little line on the side to illustrate that is a V. So you got to really make that really sharp that is a V, not a frequency. And what basically that says is that shows that anything, I'll bring this up a little bit, and this is a little cumbersome, shows that anything with both mass and velocity has a wavelength. So if we can figure out the mass of something and if we can figure out how fast it's going, it will have a corresponding wavelength. And we know that wavelengths then fall onto the electromagnetic spectrum, and there's a corresponding energy and all that good stuff. Okay. Little side note, we will go over them. I did post them. I cannot hand back your exams yet, but they are posted. Okay, top score was a 40. There were 39s and 38s, and well, there's basically a little bit of everything. I don't know the exact averages. I think it was like a 35 and a 34 in each class. So we'll go through that more specifically later, but it was very high averages. I went through a lot of stickers, more stickers than, it really hurt my sticker book. I was happy to do it, but I was like, my gosh, I'm like going through pages of stickers.
What do you need for a sticker?
An A, 36.
Would that be like a 95 or a 90 or 92.5 maybe?
It's a 90.
A minus or up, 36. A minus or up. So Rory got a sticker, it sounds like. All right, so we're going to do one equation in the lower right. I do not have the answer, but I do have the application of it. We did the other ones last class. So let's just take a look. I'm here to help set this up for you. So it says calculate the wavelength of a photon that has a velocity, a 2.4 times 10 to the 6 meters per second, and a mass, 8.89 times 10 to the negative 37 kilograms. What is the type of wave at this wavelength? So I wrote on the side, as a refresher, remember that joules are kilograms times meters squared over seconds squared. Those are the hidden units. That's why it has to be in kilograms. It's really important to recognize that.
Kilograms over meters times seconds?
Meters squared over seconds squared, yes, sir. So then I just plugged it in. So I put Planck's constant. I did the mass, 8.89 times 10 to the negative 37 kilograms. And then I put in the velocity. I honestly don't have an answer. So if someone does want to calculate that for me, that would be absolutely fantastic. Who can get it first? Who can get it first? Who can get it first? I see Layla. I see Caleb. Caleb, take it. Oh, Layla's. Oh, wait, did she make a mistake? No, she's still going.
H is always Planck's constant.
Yes, sir.
So is the answer?
What's the answer? What did you get?
I got 3.11 times 10 to the negative 4.
To the negative 4? Okay. Is that Caleb confirm?
I had something else, but I wouldn't count on it.
Okay. Kevin, you get it?
Yeah, it's probably not right.
So much confidence. Katie? You got, Katie, so we got one confirming? Okay. If I get the same answer twice, I'll take it. So 3.11 times 10 to the negative 4 meters. What type of radiation is that? 3.11 times 10 to the negative 4 meters. What type? Infrared radiation.
Ears.
Or What? More?
Answer.
3.11 times 10 to the negative 4 meters.
Double that. Gosh, that's
All right. So we're going to keep going. Today's kind of a power day. We're just getting all the information that we need. I really apologize to some of you that the last like 3 weeks, people kept asking, what's next? What's next? And I said molecular geometry. I got a little confused because I knew we were revisiting orbitals and things like that. But we are actually doing the molecular geometry next chapter. We're getting back into orbitals this chapter. So no geometry yet. For those of you that don't like the word trigonal bipyramidal or octahedrals. I think they're kind of fun. All right. So last year and on later this week, I'm going to pull it out, but I can't do it in here because it's too difficult with the space to be able to see the emission tubes. But we have emission tubes that excite gases inside, like it's called an emission tube, but it could be a cathode tube or just basically a tube that's a vacuum that only has that gas inside of it. And we see what light is emitted from it, and we take diffraction gratings, and it causes it to show up in specific lines. Those lines prove that there are actual energy levels because the electrons jump, and when they fall, they emit a very specific wavelength. And every time they fall from one energy level to another energy level, they'll emit a different wavelength. So that's why if you see different lines, you'll see the evidence that there are multiple variations of where electrons can jump to and then jump or fall back down after they lose that energy. So two really big terms, and they're very they're descriptive in nature. Ground state, it's the lowest energy state for that atom. So the electrons fall in the ground state. That is where, if you ever get a question, which we will start having in our packets, give the electron configuration of the ground state. Well, that's the normal configuration that we would know. So like if I said sodium, and we're going to review all this by the end of the week, sodium is number 11, it would be like 1s2, 2s2, 2p6, 3s1. If you're like, whoa, I need a little refresher on that, we'll have that. But that is the ground state. It's where they all would fall into place at the lowest energy. Excited state is when an atom has higher potential energy than its ground state. And I know it's kind of a generic definition, but the electrons get excited, they jump up, and now they're in an excited state. Where are they? We don't always exactly know, but we know that they are at a higher level than where they would be at a resting lower ground state. So a couple just items that we're going to talk about. There's not a lot on here that we have to write, but Niels Bohr did a lot of work in energy levels, a lot. He really contributed a lot to the atom and its structure. So the picture on to the right, I would suggest labeling some of that. So it's just a picture of some different levels on an atom. It's very simplistic in the fact that it's just showing them as a circle. We know that electrons are not necessarily traveling in a spherical pattern. It's more of actually like a wave around the nucleus. But it says energy absorption. So what that basically means is that wave on the left, that line, that some sort of energy source is going in. So that's why I wrote like that is referring to then something's going to be excited. And then after that electron jumps and it falls, what I wrote on the other side is where it says light emission, it emits a photon, and that is reference to where we are releasing that energy. It's releasing that energy. And I hope that does make sense at some level, like when it's falling, it has to be releasing energy. Well, there's an equation that goes with this. Now, this is not the one that's normally given, but I will show you. Yep. So we will talk about that energy in a moment. But what Niels Bohr discovered, now he did this only with hydrogen. Anything else is more complicated. We really are unable to do anything else but with hydrogen. This value will become much more clear when we do these problems in a minute. But we have a certain amount of energy that is basically required to remove an electron, and then that's based off of how far what energy levels you're removing them from. Okay, so the atomic numbers on the top, we are going to be doing hydrogen, so that's why there's a 1. and then it's basically where did it start and where did it fall. And once you see how this is applied, I think you'll feel very comfortable with it. It is not about memorizing. You do not need to memorize the 2.178 times 10 to the negative 18. Okay? We need to be able to apply it. So I'm going to jump right into the first of the two problems I believe I have. So please don't do the other one. Don't even look at that one. So it says, and I hope this makes some sense. It says calculate the energy, and don't just copy, kind of do this with me. Calculate the energy required to move the hydrogen electron from energy level 1 to energy level 2. And next chapter or next page, we're going to learn that N is the energy level, if you don't already. It says find the wavelength of radiation that had to be absorbed by the electron. Okay, so it went from 1 to 2, so the energy had to go into that electron. Okay, so it's going from 1 to 2, so that's why we write the 2 is my final, the 1 is my initial, and I will say you have to be very careful. This is now 1/4 minus 1. Emily?
Are both ones on the top of the atomic number?
Yes, it'll always be, and it'll always be 1. You can always lie and fake this for other atoms, but it's not legitimate. It's only for hydrogen. So you will see this equation sometimes where they'll just actually throw this underneath, and they'll take this number and actually just divide the N final minus N initial. But it's got to be squared. So when you get it all done, you get that, that energy, okay? And I'm not going to finish this problem right now, but I wanted to show you where you have to jump to the next level on this, is that you have to recognize what a problem is able to give you and what it's actually asking. And in this case, it's giving you all the information to be able to determine the energy. But the question is, what is the wavelength? So then you need to recognize, wait a minute, I have energy, I can determine wavelength. This is going to be used a lot. Now, that's not exactly the equation we had, right? It was E equals hc over wavelength, but you can just flip those two. So then I take that, I plug it in, I will eventually be doing hc over my new energy, and that would be a wavelength that would correspond to that. Now, just in case you're like, wait, I don't understand. I thought when an electron falls, it emits in a wavelength. It's true, but this is the amount of energy that went into it, so when it falls back, that's how much energy will be released, and it'll have that wavelength corresponding to it. Okay? So that one is kind of just a straightforward plugging in the two energy levels and we move on. This one would be very tricky, and I've seen this one actually on different kinds of AP questions. It says calculate the energy required to remove. And this is why I bring this one up to show you what the heck this number actually refers to. To remove an electron from the hydrogen atom in its ground state. So I'm actually going in and I'm going to remove that electron completely. So that's all about ionization and creating ions, okay? So what we do, we use that 2.178 again, and then here's the thing. It's final minus initial. So hopefully the initial makes sense, and again, if we were in the room with the smart board, I would be slowly writing this. I just don't know how else to do this in here. So that's my 1. Why do I have infinity? Because I'm taking it out. So it's like it's unlimited energy level. So what does that basically become after it's all said and done? I mean, this is going to be an extremely small value, right? It's basically nothing. So this whole thing is more or less -1 because this is gone. So this is just -1 over 1 squared, which is just 1. So the negative times the negative, oh, wait a minute, that's this number. So that number was determined by Niels Bohr that's how much energy it takes to remove an electron completely. So I hope that makes sense that this number is less because they are only moving it from the first to the second. Like I'm trying to get it away from that nucleus. There's an attraction. I'm trying to get it all away from that nucleus, and to get it completely released from that energy, that's how much it takes of energy to actually literally get it out of there. This one, I moved it up from 1 to 2. It took some energy to get it out, but it wasn't all of it. Okay, so that's the maximum amount that can exist. If you go over, it's like, I don't know what you did if you made something new or plugged it into something else, okay? So that is a little bit of that equation that you will need to be able to do. All right, moving forward quickly, and I just want you to have an appreciation of these two. guys, and we're not going to go into too much. Schrodinger. I don't know if you're in physics and you've talked about Schrodinger's cat, or if you've heard of Schrodinger's cat. We'll talk about that in a second. But Schrodinger, both these scientists, but especially Schrodinger, did some math that only a few people in the world know how to do. This is something that we don't talk about in general chem, though. If you take a look, okay, first off, Schrodinger, he's got the cool umlauts. I like that. I think my name used to have those a long time ago. Must have a whole number of half, that sounds confusing, wait, whole and then half, of wavelengths to avoid interference. What he is bringing to the table specifically, and this I hope starts to actually create a better picture of what an electron is doing in an atom for you. It's not on a circle, okay? It's not these generic train tracks. Electrons are particles, and particles behave like waves. So if you see these pictures right here, it has to match up. So an electron is going to have a certain amount of energy, and it's going to be traveling as a wave. So if it doesn't match up, it's actually going to either expand, you can call it an orbit if you want, or it'll shrink it down to actually match up to make a wave. And that actually dictates how big our electron clouds are. Less energy, the waves are probably going to be not as, they're going to be smaller in movement, and creating a matched wave will be able to create a smaller orbital. And then as we gain more and more energy, it'll create a larger and larger pathway. But it's got to match up. It's got to match up. And I'll show you a funny video in a second. But Heisenberg. Yeah, sorry, Lily.
Are we going to have to know, like, all these scientists for the test?
Always about the test. Yes, and spelling, and their birth, and their... We'll evolve that as we go. There are certain ones that if I refer to them, no, you don't... I'm not going to be like, who did this? I will say this, it does come up in multiple choice tests on AP exams, though, from time to time. So it is important to see it. But big picture idea, I don't know. Heisenberg, not the Heisenberg from Breaking Bad. If you watch that at all, that's where he gets this from, though. He has a really important thing that he came up with, and it's called the Heisenberg uncertainty principle. And this is what it is. And again, understand it and appreciate it at least this level, I hope. We're trying to find an electron. This is why we had to go to the quantum theory. We don't know where everything is. It's not as, we can't, it's so small, we can't see it. How can we be so certain? And Heisenberg basically stated we can't. You can either know the position or the velocity of a particle. You can't know both. So there's uncertainty. Like, if I want to know where it is, I'm finding this electron, I have to literally isolate it, and I get the position. But if I locate it, I really don't know the velocity, the speed and the direction, because I've done so much to alter it. A lot of people state the minute that you even observe something, you're altering it in some way. If I'm tracking the velocity, I never really know where it is. Can't know both. So there's uncertainty of, okay, we have these electron clouds and they're kind of here. There's a probability that they're located here. But that's what Heisenberg brought, kind of like, hey, slow down, guys. It's not as specific as you can say it is. So there's this thing called Schrodinger's cat. And basically, Schrodinger talked about uncertainty. And it's so much more complicated than this. But it's kind of sadistic, too. There's this cat inside this box. And there's a vial of poison or arsenic. And there's different stories of how this is specifically going, but I'm going to kind of just do a generic version of this. And you don't know if the cat's alive or if it's dead. But if you open the box, it automatically releases the poison and it will kill the cat anyway. So it's that inability to ever actually know something completely, and you have to more go on the data and the faith and it's a conundrum that we have with the atom, because if you observe it, then you alter it, but yet there's so much unknown to it. And again, I'm not going into all the specifics on it. There's a lot of cartoons about it all, but you can't shake the box. You're like, just shake it, or just look through the hole, see if he's alive. You don't know. So here, I'm going to let my good friend Sheldon explain it a little bit.
I'm aware that Leonard asked me out. Well, he didn't actually say anything, but when he came back to the apartment, he was doing a dance that brought to mind the Happy Hippos in Fantasia.
Oh, that's nice. Anyhow, the thing I wanted to talk to you about is, since Leonard and I have become friends, I was just... You want to sit down?
Oh, I wish it were that simple. See, I don't spend much time here, and so I've never really chosen a place to sit.
Well, choose.
There are a number of options, and I'm really not familiar enough with the cushion densities, airflow patterns, and dispersion of sunlight to make an informed choice.
All right, why don't you just pick one at random, and then if you don't like it, you can sit somewhere else next time.
No, that's crazy. You go ahead and talk while I figure it out.
Okay. Here's the thing.
I apologize, I didn't know there was this much lead into this, but it's okay.
Leonard had a little crush on me.
A little crush? Well, I suppose so, in the same way Menelaus had a little crush on Helen of Troy.
All right, yeah, I don't really know who they are.
Well, Menelaus was the brother of Agamemnon.
I don't care. Listen, the point is, Leonard isn't the kind of guy I usually go out with.
Leonard isn't the kind of guy anyone usually goes out with. Would you be open to rotating the couch clockwise 30 degrees?
No. What I'm saying is, Leonard might be different in a good way. Obviously, my usual choices have not worked out so well.
The last one worked out well for Kuthar Polly. He got a free iPod. Oh, glare.
It's almost getting to it.
Things don't go well with Leonard. I risk losing a really good friend. I mean, I'm guessing he's not looking for a fling. He's the kind of guy that gets into a relationship for, I don't know, like you would say light years.
I would not say that. No one would say that. A light year is a unit of distance, not time.
Thank you for the clarification.
Draft. You see, people hear the word year and they think duration. A foot-pound has the same problem. That's a unit of work, not of weight.
Right, thanks.
It's a common mistake.
Not the first one I've made today.
Okay. I think this will be my seat.
Sheldon, do you have anything to say that has anything to do with, what I'm talking about?
Well, let's see. We might consider Schrodinger's cat.
Schrodinger. Is that the woman in 2A?
No, that's Mrs. Grossinger. And she doesn't have a cat. She has a Mexican hairless, annoying little animal. Yip, yip.
Sheldon!
Sorry, you diverted me. Anyway, in 1935, Erwin Schrodinger, in an attempt to explain the Copenhagen interpretation of quantum physics, he proposed an experiment where a cat is placed in a box with a sealed vial of poison that will break open at a random time. Now, since no one knows when or if the poison has been released, until the box is opened, the cat can be thought of as both alive and dead.
I'm sorry, I don't get the point.
Well, of course you don't get it. I haven't made it yet. You have to be psychic to get it, and there's no such thing as psychic.
Sheldon, what's the point?
Just like Schrodinger's cat, your potential relationship with Leonard right now can be thought of as both good and bad. It is only by opening the box that you'll find out which it is.
Okay, so you're saying I should go out with Leonard?
No. Let me start again. In 1935,
You know how to do that? I thought you guys knew everything about computers. No. You just hit the Windows and, like, if you do Alt and Tab, you can do it this way. But if you do Windows and Tab, you do it this way. So, anyway, first off, Sheldon's not completely right. He says, only if you open the box will you know. But if you open the box, you kill the cat. So it will be dead, no matter what. So, all right, we are almost through. The last page does not have a lot on it. So if we could go to the last one. So quantum numbers. I always find, and I just found it with my general chem class last week, that people do very well on this, even if you're not remembering it all. It is a specific address to where an electron exists, and there's 4 numbers, and we're just going to kind of break those down, and I have a lot of imagery with it already, but it's not nearly as complicated as that looks. So just do the upper left first, please. There are 4 quantum numbers, and I on the right side, it says name. I put quotation marks because there are actually different names to this, like it's called the principal quantum number and the magnetic angular momentum.